Greetings and welcome to another exciting lecture in geomorphology. Today we're moving outside of the channel and going to think more holistically about drainage basins. That's right, we're going to be talking about the area of landscape that contributes water to the channel. We're thinking about different forms of drainage basins, the pattern of the streams within a drainage basin. We'll be thinking about streams that cut across drainage basin structures. So that's our goal for today in our lecture. And so the picture behind me that we're looking at right here, this is the beautiful San Ysidro area in central New Mexico. And notice what we have are some up-tilted rocks that have been eroded. Does everyone see these up-tilted sedimentary rocks here? And look, we see a nice little ridge, and I can trace that ridge all the way around to the other side, on this side over here. So you can imagine that if you're a raindrop and you fall onto this landscape, you fall inside, you're eventually going to go down to this ephemeral channel, right? And you up on the other side right here, and rain, I would slide down this slope here to this ephemeral channel. I am in the drainage basin of a small little area here defined by these ridges going all the way around. So when we talk about drainage basins, it's a really powerful and fundamental concept in our understanding of superficial processes at the surface of the earth, because with drainage basins, everything within the drainage basin, the water all flows down to a central point. So when we define a drainage basin, the first thing you need to do is define an outlet. And what we do is we define a drainage basin area above that outlet. And so drainage basin boundaries, so this is also known as a drainage basin divide. See that right here, drainage basin divide. The drainage basin boundary is essentially ridges. And so if we look at a landscape in 3D, this is already in red, but notice this line follows the ridge line. So drainage basin boundaries follow ridge lines. Sorry, that errant line on there, but we can see on the other side as well. So a drainage basin divide will essentially separate two different drainage basins from each other, and they're generally ridge lines. You can imagine a water drop falling down. It hits on one side, it rolls off one way. If it lands on the other side, it rolls off the other way. Some other terminology here I do want to highlight. Drainage basin can also be used in terms, you might hear the term watershed. A watershed is synonymous with a drainage basin. Another way you might hear watershed used is a watershed can also apply to the boundary, that drainage basin divide. And that's where the term watershed moment comes from, like an important moment. It could go one way or it could go the other way. That would be a watershed moment. So you often will hear that across the pond, that you have a watershed, which is that boundary. But here, how we often define it is the watershed is the drainage basin, and then the drainage basin divide defines one drainage basin from another. And essentially, you just pick your point on the stream and define the drainage basin above it. What we're looking at right here is just the major drainage basins within the United States. Right here, we're looking at subbasins of the Mississippi River. So here's the Mississippi River. Here's the upper Mississippi, Missouri River system all the way here. If we come over to green, this is the drainage basin we're in right here, which is the Columbia River drainage basin that drains out to the Pacific Ocean. So Columbia River drainage basin. I want to note a really interesting feature here that we see in the middle of the Western United States, this pink area right here. Everyone see what I'm circling? Notice that there doesn't appear to be a link to this to another drainage basin draining out. That's what we call the Great Basin, and the Great Basin is an internally drained basin. So internally drained basins are basins that have no outlet. And so a great example would be the Great Salt Lake. So here's the Great Salt Lake on the west side of the Wasatch Range here in Colorado. So in Utah. So here's the Wasatch Range right here. And then any water that rains and falls in the Wasatch Range, at least on the west side, drains down into the Great Salt Lake. But in every direction, the water drains into the Great Salt Lake. There's no outlet. So we call this internally drained, and that's why the Great Salt Lake is so salty, because water drains in, it can't flow out. So the only way water gets out of the Great Salt Lake is through evaporation, which then will turn the Great Salt Lake saltier and saltier is you deliver more river water that has dissolved ions in it. The dissolved load, excellent. The dissolved load stays, the water evaporates out, and the water gets saltier. So that's what we call an internally drained basin. The Great Salt Lake is a great example, and it's part of the larger Great Basin that is most of Nevada, which is a series of internally drained lakes. Okay, when we think about drainage basins, we can also think about not just the water of movement through the drainage basin, but the movement of sediment throughout the drainage basin. That's a reason why drainage basins are a really important concept. We can catalog sediment, the sediment coming into the drainage basin and the sediment leaving the drainage basin. And so what we're looking at here is a sediment budget with up here on the upper side, these are our sources of where the sediment comes from. And then our sinks are where the sediment is being stored down here. We end up with a boundary between sources of sediment in a drainage basin and sources and sinks. So in this case here, we have sediment coming. If we look at a point on the river, we're going to have sediment coming in from tributaries, sediment eroded in from upland sources off from hill slopes, sediments coming in from landslides. All these add in. And then once that sediment is in the drainage basin, we're going to store some of that along the hill slopes as colluvium. So that would be all the sediment kind of stored here on the sides of the hills. We'll have some sediment stored on the valley bottom. So that's down here, this area in red here, that's sediment storage on the valley bottom. And then finally, some of that sediment evacuates the drainage basin, leaves the drainage basin as sediment yield. So sediment budgets are a really important, powerful way that we can understand the movement of sediment throughout the landscape and thus start thinking about the erosion and changes in erosion of the landscape. In our next class, we'll look at some specific examples of sediment budgets and how humans have altered them. Okay, let's talk a little bit about drainage basin patterns. When we talk about a drainage basin pattern, we're talking about the orientation of tributaries in main stem channels. So basically the orientation of the rivers within the drainage basin. So here we're looking at the Wallowas here in the Wallowa Range in Oregon, and we have this main channel right here, this big long stream right here, the Lostine Creek. And then on the sides, we have smaller tributaries that all come in at basically at right angles. Everyone see that here? So this would be a particular drainage pattern. So let's talk about the different types of patterns. The most common drainage pattern that we see is what we call a dendritic network. So a dendritic network is essentially where you have tributaries coming in at different angles and you form kind of a tree with lots of small tributaries coming together, and two tributaries come together and form a larger stream and then a larger stream. So we call this a dendritic network. And so this is a shaded relief image from Pennsylvania and looking at the dendritic network that's formed on the Allegheny Plateau. So the blues here are the main stems, and then all these little small kind of trees here are small little tributaries that are falling or that are flowing into the main river. So a dendritic network. This is kind of the most common type of drainage basin pattern we see. When you see drainage basin patterns that aren't dendritic, it oftentimes is telling you something about the underlying geology that is controlling the pattern of the tributaries. And so an example would be a trellis drainage basin. And so a trellis drainage basin is when you have a single trunk stream that flows down, and then along that trunk stream, you have other streams coming in. So imagine me walking towards you right now. I'm the main trunk stream, and as I walk down, I'd have small streams all about the same size coming in. So that would be a trellis network. And so trellis drainage basin, here we're looking at some, also from Pennsylvania, where we have faulted and folded terrain. And so we end up with these ridges associated with synclines. And so you end up with a main stem going down the middle of the syncline and then smaller tributaries feeding in. So that would be a trellis network. Another type of stream network would be a rectangular network. And so rectangular networks are when the streams come together at right angles. And so right angles would be a rectangular network. And so we're looking at some pictures here of some right angles in the stream. Here's a right angle right here. And we can just see this kind of pattern here showing these right angles. These are common in locations where you have a fault and fracture network that's going to produce right angles in the landscape. So if you have a set of faults or joints that are at right angles to each other, you'll get preferential weathering along those joints, and the rivers will flow along them, and you'll end up with a rectangular drainage basin pattern. Okay, our next type of pattern is what's known as a radial drainage basin. Radial drainage basins are different because your rivers are actually all flowing into different drainage basins. So they're flowing away from each other as opposed to tributaries coming together. And so the classic example of a of, of a radial drainage pattern would be a stratovolcano. So here we're looking at Mount Rainier. You can see all these lines coming off. These are rivers coming off from Mount Rainier in different directions. And so the water's all flowing away from a central point. This is a classic example of a radial network here in the state of Washington with Mount Rainier. Okay, the next term I want to talk about are what we call transverse drainage basin patterns. So these are really interesting. Transverse drainage basin patterns are when we have essentially our drainage basin that's going to cross a major geologic feature. And so the classic example of a transverse pattern would be this river. This is looking in the Himalaya. Behind us is the Himalaya Plateau. And we're looking at a river network that's cutting across the Himalayan range front. Does everyone see that right there? And so one would predict that essentially the high topography of the Himalayas would be the drainage basin boundary. But in fact, what happens is water that falls on the other side of the Himalayas will flow down into this river system and flow out. So this is the Ganges River here. And again, this is telling us something interesting about the geomorphic history of a landscape, these transverse drainage basin patterns. Let's talk about how these things can form, because it's really quite interesting how you can get these guys. Okay, the first type of drainage basin, transverse drainage basin pattern is what we call antecedents. And so in the case of antecedents, the drainage basin network, the pattern of the river actually predates the geologic structure. So in this case here, we have a stream that's just flowing along a landscape. And then what we have here is we get faulting. And we're going to pop up this block right here. We pop up the block. And now the river, basically, as the sediment, as the mountains are building, the river can cut down into it and cut across that structure. So a classic example of this would be right in our backyard, the Horseheaven Hills, which is essentially an anticline that we get that goes north-south. And so here is the Horseheaven Hills right here. And then look at the Columbia River. Columbia River looks like it could care less about the Horseheaven Hills. It flows right through them. Well, how does that work, right? Streams can't flow up and over a drainage basin. And so in this case here, likely the path of the Columbia River predates the uplifting of the Horseheaven Hills. And so the river's there, and then as the mountains pop up, basically the river can keep pace and cut down right in the middle of that structure. So that would be an antecedent structure. Another type of structure would what we would call superimposition. And so in this case, the river was flowing first, and then as your landscape lowers over time, it encounters a geologic structure that through weathering and erosion is exposed, but the river can cut through it. So what we're looking at here on this side, is that we have some sort of hard rock associated with an anticline. And then as our rivers cut down in, our rivers are cutting down in, our landscape's lowering, this structure gets exposed. And let's say this is a harder rock here. So the landscape can't erode as much at this, but the river can cut right through the middle of it. So the river cuts right through the middle, but leave the sides high. So this is what we call superimposition in terms of transverse drainage basins. Everyone kind of see the difference here between this and antecedents? Antecedents is when the structure didn't exist and then it pops up new. Superimposition is the landscape lowering and encountering structure. Okay, a great example of this would be here on the Susquehanna River in Pennsylvania. So here's the Susquehanna River, and look how it's just slicing through these folds. Everyone see these folds right here and rocks associated with the Appalachians right here? So the river just cuts right through those. How does the river cut through those? Well, the river path was set, and what's happening is as the landscape is lowering, we're encountering these structures and we end up with sandstone ridges here, but we get weathering. And so you can weather out the soft shales in between the sandstone ridges. And that all gets flushed away and you accentuate that pattern. So this is our superposition. Okay. Our next type of event is what we call an overflow, where we have two separate drainage basins. So we got one drainage basin over here, one drainage basin over here, and we basically fill up this. So we start essentially creating water that's going to flow over the top of this. So our water is going to fill up and over the top. Because of that, you'll get erosion at that overflow point right there. So we get erosion at the overflow point, and we can cut down in. And so we end up leaving that bedrock high because we can only focus that erosion right at the right there, right at where the overflow happens. So that would be an overflow. A great example of that would be the connection of the Colorado River in the southwestern United States. So here's the Colorado River flowing down. So there's our Colorado River. And what happened is the Colorado River used to not be all connected. It used to not be integrated. You had a series of lakes. And so right here at this location near Parker Dam on the Colorado River, we essentially had one of these overflow events, and the Colorado River flowed over and cut across these mountain ranges here and integrating the Colorado River. So this is what we call a overflow. Okay, our final type is similar to overflow, but it's where one stream cuts into a drainage basin divide and captures another river system. We call this, yes, you guessed it, yar, this is stream piracy. And so with stream piracy, what we're looking at is we've got a drainage basin here, and we're kind of right where I'm trying to erode. So right here, we're eroding on our drainage basin, and we cut through the drainage basin divide and we capture another drainage basin. So this would be what we call stream piracy. And with stream piracy, again, it allows us to have a high and then a stream that's cut through that high. So stream piracy. So a great example of this would be here in Colorado. What we're looking at is the former course of the Huerfano River. So here's the Huerfano River here. Huerfano River, and these are a series of terraces over here of the Huerfano River. So the Huerfano River used to flow down in this direction, but what's happened is a smaller creek, Muddy Creek, was actually eroding back up the landscape. So here's Muddy Creek over here, and Muddy Creek cuts all the way back to right here, and it captures the Huerfano River. And now the Huerfano River flows down the old Muddy Creek off this way. And we essentially we've captured this stream and we're cutting down and we've abandoned this high old landscape. So this would be an example of stream piracy. Okay, so those are our transverse drainage basin patterns. Let's move on to another couple of topics when we talk about drainage basins and how we characterize the morphology of drainage basins. The next term I want to introduce is what we call the Strahler classification system. So the Strahler classification system is how we catalog the streams and tributaries within a drainage basin. So in Strahler, the smallest streams you call one. We call these first order streams, either the smallest streams in the drainage basin, and then at where those two meet, that is a tributary junction, and the stream that forms from those would be a second order stream. So here we've got one first order meeting a second at a tributary junction, and below that we have a second order stream. Where two second order streams meet, we would go up to a third order stream. Notice that in the Strahler classification method, that when we add these guys together, if a third order meets another first order, it doesn't become a fourth order. It still is a third order. It's only if you add stream orders of the same size together that we end up with larger streams. So because of that, you really don't see stream orders below much bigger than 6 order streams, because there aren't that many big streams that come together. When we think about stream orders, what we see is that the length of the stream increases with the stream order. So higher order streams end up with longer stream length than lower order streams. So this would be the Strahler classification method. Another classification method is what we call the Shreve classification method. And so in the Shreve system, when you add two ones together, that becomes a two, where two second order streams come together, we end up with a fourth order stream. You add those numbers together. So this is called magnitude instead of stream order, stream magnitude. Whew, there we go. Shreve. So that's where the Shreve magnitude comes from. In this case, the area of our stream increases with our stream magnitude. So the larger magnitude streams have larger basin areas. Okay, so we get two types of channel ordering. Commonly, what you'll mostly hear is this Strahler method. People refer to the Strahler stream order, first order, second order, third order stream. Okay, so let's move on a little bit here. And I want to review a topic, as now we can think about it in terms of drainage basins, and that's the topic of hydraulic geometry. We covered this in our lectures on channels, but I want to return to it also because this is the lab we'll be working on, is thinking about hydraulic geometry. And so remember, hydraulic geometry tells us a little bit about how streams change as they move down the drainage basin. So what we're seeing here is that, let me duck down. We've got drainage basin area here on our x-axis on all of these streams. The drainage basin area. And then as drainage basin area increases, so due to the characteristics of the streams, the velocity of the stream, the depth of the stream, and the width of the stream all increase as a function of drainage basin area. So keep that in mind. Sorry about that. And we are back. So we just finished talking about hydraulic geometry, the importance of hydraulic geometry. And now the last part of our discussion today, I just want to focus on kind of how the drainage basin changes in terms of the morphology of the drainage basin from the uplands in the drainage basin to the lowlands. And so essentially, when we think about a drainage basin, we're going to get, let me get out of the picture here so you can read this. We're going to get essentially a continuum of changes as we go from the top to the bottom of the drainage basin. And we generally think about the upland sources is our, go this way, our sediment sources, where the sediment is coming from in the drainage basin, and then the lowland portions of the drainage basins are the sinks. Let's look at a graphic here to think about this. So here's our continuum going from the top of the drainage basin here all the way down to the lowlands. So this is uplands to lowlands. And so up in the uplands of the drainage basin are where our hill slopes are. And then we're going to have confined channels kind of in the midpoint in the drainage basin. And then the lowlands, we're going to have big, broad channels with big, broad floodplains where we can stack up sediment in them. So that's going to be the bottom of the drainage basin. And so when we think about this, we can think about it in terms of channeling coupling, how the channels are linked to the side slopes. So up towards the top of the drainage basin, you're going to have your hill slopes that are directly connected to those small channels. And so you have tight coupling, buffering, and resilience. And so we're going to have less buffering and resilience up high because of that connection between the channels. And then after that, we'll have our floodplain storage of sediment and water. And so that increases as we move down. So if we look going down here, we're going to look at active geologic processes and landscape characteristics going from the uplands to the lowlands. So first here, in terms of our active geomorphic processes, there we go. Let's get that all out there. So we'll have lots of erosion at the top of these, debris flows and avalanches up in those hill slope sections. And we're going to have essentially often frequently saturated ground as we have more rainfall up in the mountains. We'll have high magnitude disturbances like big landslides. And beside the streams, really, you will have more stable streams that are infrequently impacted by things like debris. That's going to be up in our uplands. As we move down, we'll be down in kind of our confined channels where we'll have debris flows that are being deposited, not where we have initiation of debris flows, and where channels are going to be filled up and overbanking. And in terms of landscape characteristics, we'll have a kind of confined channel, so we won't have much habitat on the channel, and we'll have infrequent high magnitude disturbances associated with floods again. And once in a while in these confined reaches, we'll have bed mobility when we have big storms that can get stuff rolling along. As we move to the bottom, we end up with our lowlands where we have wide floodplains and the streams can meander across and deposit sediment. The streams will have channel avulsions, channel migrations, and flooding. And here, because we've got finer particles and big discharges, we'll have more frequent flooding, more or excuse me, more frequent movement of the bed during smaller magnitude events. Um, and we will have basically complex channel habitat because you'll have all these side channels and floodplains. And so you end up with larger riparian zones and more frequent flooding on the side. So that's kind of how we think about drainage basins going from the uplands to the lowlands. So we can look at another picture of what this looks like. So here we start in a drainage basin up in the uplands, up in the colluvial valleys, and then we move down into the bedrock valleys. So these would be bedrock channels, and then into the alluvial valleys. And then from the alluvial valleys, we end up where your drainage basin connects out to the oceans, where you'll have your estuarine valleys, so where we have estuaries. We'll talk a little bit more about those when we get to coastal processes. So we can think, another way to think about this is the slope as we move from the uplands down to the lowlands. And so at the very steep, kind of right along the ridges, we'll have very low slopes. And then as we get to the steep parts of the landscape, the colluvial parts will have steep slopes. And then as we move from the bedrock down to the alluvial valleys, our streams will generally flatten out. And that gives us kind of a concave profile for kind of stream long profiles as we go from the steep uplands down to the flat lowlands. You'll get a concave stream profile. All right, that's all I've got for you now on drainage basin patterns. Good work. We'll revisit some applied concepts in drainage basins in our next discussion together. So have a great afternoon, and we'll